Well, hello everybody. Good afternoon, good morning, good evening. Welcome to the Propeller 2 live forum on September 9, 2020. Today Chip is presenting audio effects processing with the P2. And before we let Chip loose, because I know this is going to be a lot of fun, and he's going to talk a lot and share a lot of cool stuff. Here's the P2 Edge, latest pictures from this morning, looking good. And it's getting routed right now. So coming along. And if you want details on it, you'll need to ask Chip because I was not in the last meeting. And there will be a breakout for it. This is an old image. So we're shooting for November when we release the P2 formally, along with a few other goodies that are happening. John, can you tell us about the wonderful things that are here? Unmute yourself. Sorry, I didn't give any warning.
No worries. As I've been, doing, I've gone through code that I've written in the past and that clients are needing now and porting it to the P2. So the first one in the circle is a really simple object, but works nicely. There's two there. The Max 31855 is a thermocouple interface. It works with SPI. Super easy. And that's working as a little demo program that shows how to read it. And the 1638, TM1638 is it's a kind of a LED driver with key input, and hopefully I can make this show up on my phone here. Let me try this. This green screen's killing me. Anyway, they're very inexpensive, but with a few wires, you get a bunch of 7-segment LEDs and some buttons. And so that driver takes care of that. There's two circled the same thing. Yeah, they're all the
same. Okay.
Yeah,
cool.
Those are
So also, since John is publishing all of these objects all the time, we really need to lend him continual support. Although he's probably embarrassed by my bringing this up, but I think it's important. So I will find the chat when Chip gets started, and I'll paste in a link here so we could send John some money.
If I may say, people were incredibly kind and generous after my presentation. And I think I sent everybody thank you notes. If I missed you, forgive me. But thank you very much to all those people who sent gifts.
Awesome. And the Propeller 2 newsletter. I don't know, I think most all of you are here, but this is how we're communicating with the P2 users. And there are just under 400 people on that list. So I'm going to drop this into the chat. Chances are if you found your way here, then you received this already, but here's the link. So you can go there and sign up, click on P2 Community, and then you'll receive only about 1 mail a week, but of course you're going to get my general email as well, which is all kinds of other stuff. So more email, please. Okay, moving on to Chip. Chip, ready to go? And do you have code to share, or is it posted? Maybe you could let us know on that first. Get that microphone unmuted. Still got to press that button. Hang on, Chip. We aren't hearing anything yet.
Oh, how about now?
Okay, now we got you.
All right. Where's Michael? Is he here today? Michael von Sarvash. Because I was going to mention something.
Not here. Midnight by him.
Right. Okay. Anyway, should I just get going?
Yeah.
All right. So I've always been interested in audio stuff, and what I've done is I've made some pitch bender algorithms, and I have some things to demonstrate here. Let me see if I can open Core. Okay, here we go. So I have a little program here. I got to share my screen here. Just a second. Oh, I wish I could just share an app. I'll try to share. Let's see. Oh, where is it? Um, maybe I'll just try to share my big screen. Okay, can everybody see down at the bottom here, there's a peanut window that I'm moving. You might have to zoom in on it. Does anyone, any problem with doing that? I'm looking for your faces.
We can see the peanut window. The text is pretty small, but we can see it.
Okay, is it possible, Ken, it's possible for them to zoom in, right?
Yeah, they can zoom in by clicking on View Options and then Zoom Ratio on the top. However, it does make a cruddy video that's recorded on Zoom.
Okay, then let me try doing something else here. Sorry about all this. Stop share, and then I'll do a new share. I'll try to share just the application.
The YouTubers get very upset.
Yeah, I want it to be legible. Okay, now can you see that better?
Perfect.
Okay.
Yeah.
All right. So you guys are familiar with, like, if you want to bend pitch downwards, what you could basically do is slow time down, right? And if you want to bend it upwards, you can go faster. So if you have a circular buffer and you're writing samples in at one rate, I'm going to start this program here. Hopefully it runs. Let's see. It's stalling. Why is it stalling? Oh boy. All right. I think I'm going to have to. All right. Sorry, guys. I've got a problem here. We're going to have to look at the screen. For some reason, I can't share this actual application. So I'm just going to have to share my screen. But I've got a lot of stuff to show you. All right. So let me share my screen.
Do you have another
All right.
monitor?
So if you could try to move down to the bottom, that would be best.
Yeah, I just dragged it up so I could see it.
Oh, okay. All right. I could put things. Oh boy, now my desktop has disappeared. All my icons are gone. I can't get to. Well, here, maybe we can just run the thing from here. Okay. All right. So this is going to be large, right? If I move it down here, can you guys just zoom on this section here?
I was on it. I lost it.
Okay. Let's see, I'm sharing this big screen. You should be able to see at the bottom here, there's a peanut window.
Yep, we can see it, Chip.
Okay, and can everyone zoom in on it? Zoom in on that region and ignore the rest? I wish it was possible to just share a region of my screen. That would be quite good, but I don't think we can do that with this app, right, Ken?
I've not seen that.
Okay, so I'll just work from here. I'll work at the bottom of the screen here. So we see here, let me see, can I run this? Okay, there we go.
I was under the impression that you could share a window, but if that doesn't work, then I guess we're stuck.
I can share a
Thing's
window.
got like lots of windows, so it can't deal with that.
Yeah, well, even if I could put everything inside, what happens is my application for some reason tends to lock up.
Okay, before you proceed, Chip, just for Sirth and for anybody who's having trouble seeing it, go to the top of the Zoom meeting window, click on View Options, and then Zoom Ratio, and then pick one, and then you can slide this up and down.
Yeah, and you want to go towards the bottom of the screen.
So you can just put your little hand on it. I'm using 100% and I can see it all really nicely. Just will not make a good video for the YouTubers. But
yeah, we need to get set up, Ken, so that we can actually put stuff together that is visible, you know, and then
You need to get a smaller monitor so that you can just share that monitor.
oh,
Thanks,
yeah,
Roy.
you
Your
know,
big giant monitor.
okay, should I do an emergency procedure here and just lower the resolution? Well, no, then this screen's not going to fit. I need this many pixels to show these things. This is how they're formatted. But can you guys see this animation going on? You see like a...
We can see it when we're zoomed in, yes.
Okay, all right. So what we have here is a circular buffer, right? We have a head and a tail. So we can see these things are moving at dissimilar rates, right? The tail is going faster than the head. And if you look over at the oscillograph, you can see that the head data The head's writing a sine wave into the circular buffer, and then the tail is reading it out at a higher rate. Do you see that? And periodically, the tail crosses the head, and when that happens, we wind up with a discontinuity in the tail data, which is green.
Hey, Chip, before you continue, just so we can get a better YouTube video, John just posted how you share a portion of your screen.
Oh, okay.
So maybe we can do that. So I'll guide you through it. Click on Screen Share button.
Okay. Well,
And
I gotta
then,
stop this share, right?
yeah, stop this one. I think it'll be worth it if
Okay.
we just try to get this right. So share screen and then the Advanced tab,
Okay, share screen.
Advanced Sharing Options. I haven't looked at this, but I bet it works.
Oh, advanced. There we go. Okay.
And then
Portion of screen. Okay,
there you
we
go. Only took us 5 meetings to get this straight.
We're all
Yeah.
professionals here, right?
All
Very
right. so
professional.
yeah, this is not our strong suit yet.
Yeah, you're on your way, but you got to widen it now.
Yeah, that's much better, but yeah,
There.
oh, way better.
Awesome.
Okay, now we got it for once and for all. This is great. All right, go ahead, Chip.
Okay, so what we have here is animation. So I've made all these debug windows that can show things in different formats, right? We have an oscillograph on the right, FFT on the left, a spectrograph, which is like an intensity FFT with a rolling history, that red thing down below. And then in the middle, we have this, this little animation. I just used the plot. I have this thing called plot where you can draw any arbitrary stuff you want. You can do it in polar format or Cartesian format, so it's easy to put all kinds of neat little animations together. And I'm hoping, kind of thinking anyway, I've got to refine this a little yet, but in the long run, I'd like for objects to be able to contain, like I think Michael Summers said, just call it doc. You know, these like, we have dat, pub, pry, we could have one called doc. And in it, you can put a whole bunch of spin code that generates these animations that will be ignored during normal compilations or even debug. But what you can do is you can document with animations how your objects work in case you have concepts to convey that are a little more complex than what a picture can show. I mean, a picture is better than words oftentimes, but an animation is even that much better than a picture. So I'm running 4 of these windows now. So we can see so the idea here is I'm just demonstrating this concept of pitch bending, where we have a circular buffer, we're depositing samples in at a rate of 1. So the guy depositing the samples, he advances every sample to the next location. The tail guy has a pointer to this circular buffer, which has many subbits. So he has a lot of control over what his exact rate is. So only the upper bits of his pointer are actually used to address data in the buffer. So we can see right now we have the tail going faster than the head. It periodically passes the head. And we can see this conniption that occurs when this happens. We have this discontinuity. Like if you look in the middle of this oscillograph now, you see that sharp rise. That's like a step function because the data crossed over. And I have this thing set up here. I can make, if I uncomment this, then I'll make it go slower, right? So we'll do this, Control F10. Now the tail's going slower. So we're slowing down the signal that the head is writing. And, but watch what happens when we cross. Whoa, big problem there. So we can't have that in any kind of real application because what it's going to do, it's going to create all these clicking sounds in the output. And it's not desirable. So I was thinking, like, how can we do this? How can we get around this kind of problem? And I've been back when I was in high school, I had an Apple II. I was working on pitch benders and things like this, but it never occurred to me that I could do anything other than, you know, live with these kind of steps in the output. But back then, the audio quality, we only had 8 bits anyway. It was so poor that it was not really that big of a deal. But now we can do a lot better than that. So we want to make something that works better. So what I figured we could do is do this another way. Let me load this other program in. Let's see. It's called Crossfade. Now this one uses a little bit different of a concept. What it does is the tail buffer is actually going to be, you're going to take readings from the tail and then the opposite of the tail. And you're going to crossfade between these two these two sample points, right? So really all you do is you just, to get the opposite side of the tail, you just set the MSB of your counter or toggle the MSB, and that gets you to the other side of the circular buffer. And then we use weighting so that you can see now when the tail crosses the head, that is completely faded out, and the other side of the buffer is faded in. So we crossfade between these two things. So if you look on the oscillograph, you can see here there's all kinds of, the red trace is the head, right? It's depositing the sine wave into the buffer. And then we have the tail data in cyan, and then the opposite tail data in yellow. And then you can see that these discontinuities are occurring every 180 degrees. And what we have here, though, is we've computed this fade. So you see this like lighter, what would you call that? A triangle waveform. So this is saying how much of the cyan, the dark cyan says how much of the cyan to use, and the brown says how much of the yellow to use. And you can see they're 180 degrees out of phase, and it correlates with what you see in the animation where you have the tail and the head. Now, if you go to the bottom of the oscillograph, you can see the two modulated waveforms in dark cyan and dark brown, and then they're summed together to create the final output, which is the light green. So now you can see we're able to bend pitch without these step functions. And I can slow down. Let's see, I had this thing set up. Yeah, if I want to go the other way, I can comment that out, rerun this. And we have to.
Sorry, I just want to say this looks fantastic. Have you actually listened to this? Like what it
Oh
sounds
yeah. I got a whole thing set up. I'm going to show you. If you can see my keyboard over here, I made a MIDI app, so you'll see. I did. In fact, I didn't start that program till yesterday to do the whole fading, because I've been so busy just working on all these like these debug displays. Anyway. So you can see here now we've got a slower, right? We're slowing time down, and we don't have any step functions, no discontinuities. And if you look here at the, over on the left, or at the spectrogram for that matter, the FFT data, you can see it's very consistent. There's none of these noise events. Like if you noticed on the simple pitch bend where it was just, the tail and head were running over each other, and there were these step functions, you'd see these periodic disruptions to the spectrograph data, which is just an indication you're going to hear an anomaly when that happens. But now we have this smoothed out thing. And so now we can have dissimilar rates. The head's always going to move at one sample location, right? Because it has to put samples into the buffer to concentrate. We can take them out with this tail function at any other rate we want. And the cool thing.
Question?
Yeah.
Since you're at tail and opposite of tail, does this imply that your buffer size has some relationship to the frequency of your information?
Oh, you mean so we don't get like cancellations and things?
Right.
Yeah, we could get cancellations. If you had a wave in there the head was depositing that was like, what would you say? It would have to be a harmonic of the buffer loop time, the buffer loop frequency. Right. Then we could get standing waves and they cancel each other out. But in practice, I don't think it really happens that much. And if it did, you would only notice a decay in amplitude. You wouldn't notice like some nasty noise or anything. But you can see how that thing is sliding. Like, I think of it's like it's kind of doing a dance where you see the green gets out of the way of the red, and then it comes and it spins around. And what we could do is I could do this animation. Watch this. If I stalk the head down here, right? If I comment out this little instruction that increases the head, then what we can see what happens, what the relationship looks like, if the head is static. In fact, it's kind of slow, right? So let's do this. Let's comment out, let's put this wait 20 milliseconds down to 2. Now you can see it a little bit better. And so really that green thing is bouncing back and forth, but it's also rotating. And then when you get the whole thing working together, Anyway, the cool thing about this is that this equation for computing the weighted values for opposite and tail, it's a simple equation. It doesn't matter if one's going faster than the other. Whatever the relationship between the two is completely determines the fading factors. So that's kind of something that's not so complex. Anyway, I'll show you the bigger thing here. So you get the concept, right? You can crossfade between these two buffer points and you can avoid these distortions that you'd otherwise hear. So now let me load in this question.
Could you say something about the choice of the triangle function there instead of like a sinusoidal function?
Oh yeah. Okay, hold on. Let me get back out of here. So you're asking like, why did I use these triangle waves? You know, it was just simplest. We could have totally done a sinusoidal thing, and I should try that. You know, I wonder if it would make much of a difference.
It might not matter. Yeah.
Yeah, it may not matter. Yeah, because if you look at something like that, you think of those sharp changes in the what would you call that? The derivative are going to create some kind of perturbation that you've noticed with your ears, but I don't know that I don't really notice it.
Yeah, no,
but I mean,
okay.
I'll try it.
Looking at the green wave on the bottom, it looks like a really nice sine wave. So it doesn't look like there's any artifacts from the underlying triangle or a triangle synthesized
yeah,
function.
that doesn't.
Yeah, it could. You know, you guys, I'm going to publish this. I didn't have time. I had some problems with the main program I want to show you, and I was working to the last minute. I barely got it working again. I broke it because of the way I was handling the MIDI stuff, and I had to make it work again, so I barely got in. So I didn't have time yet to put the file up, but I'll put it a little later.
It looks like the green output is a slightly lower frequency than the yellow and cyan outputs. Like if you look at the shape of the sine waves, the yellow and cyan ones look like a slightly higher frequency than the green one.
So the way to check is look for the peaks, the relative peaks. If you can see two peaks, in fact, let me comment out. Let me make it turn faster so we can tell better. All right, now if we can look at the peaks. Look at the cyan. Okay, now we're not getting the crossover interruptions as often, so you can see both. This way they look identical.
Yeah, they look very close here. I'm just talking about when it's slowed down, it looks like it's slightly off.
Yeah, well, the reason it did is because we were not able to see a complete cycle of either the cyan or the yellow because of the disruptions from the crossing.
Yeah, but you could tell by the slopes of the lines. I suspect that might be improved by using sine wave instead of triangle.
It did look like the radius at the top and the bottom of the green wave is slightly stretched out compared to the radius at the top and the bottom of the cyan and yellow.
Oh, you're right.
That wouldn't be a different frequency. That would just be other harmonics on top of the fundamental.
Well, the actual peaks look like they're slightly farther apart and close, you know.
Actually, no, that's a good point, though. As long as the peaks stay relatively aligned all along, then the frequency has to be matching.
Yeah.
And it is probably the underlying harmonics that are actually stretching it out a little bit. Or
yeah.
And the shape is slightly off. Like you can see it's shallower on one side and steeper on the other side.
One thing you'll see,
the green.
You know, you were talking about constructive and destructive where it just changes the amplitude. But if you have like a sliding pitch, you'll actually hear it because it'll warble.
Yeah.
And I suspect that if you tried with the sine wave instead of a triangle wave for the yellow and blue or cyan, that you might get a slightly more accurate green wave at the low frequencies anyway.
Right. Yeah, I'm going to change it over to the sinusoidal crossfade. I think that might be good. When I first set this thing up, I figured to make it work really well, I didn't just pick up samples at the tail and opposite tail, but I interpolated between two adjacent samples with all the subbits of the phase. But actually, it didn't really make any improvement. It just slowed things down, so I took it out. But you could get really accurate with this. You know, you could take two adjacent samples, like at the tail and tail plus one, and then interpolate between them in order to get kind of a really accurate subsample. So in theory, that should improve things, but in practice, it just seemed to make things a little muddier, so I pulled it back out. But maybe I wasn't doing it right. Maybe there was something wrong with my math. Anyway, so you guys you see the concepts here. So now I made this other program. Before I show you that, though, let me see. I have a little MIDI thing. So here's a little program I wrote. This is just in PASM, right? And all it does is it sets up the clock. It declares an RX pin. Then it does. I made a MIDI debug window, right? Just call it MIDI, and then where to put it. Oh, we're going to need that thing way lower, like let's say, so that we can see it. Let me put it down here. And then let's see. So we set up the serial pin right here, and then we wait for serial messages to come in, and then we just simply report the data to the MIDI thing, and it does the MIDI state decoding, which is really simple. You have on-node events and off-node events, and here it sends those bytes that are received to the MIDI debug window. And then it just waits for the next character. So I'll run this thing. All right, let me get this thing a little further. Why is, it doesn't seem quite right. You know, what's, hold on a sec here. Okay, that's a little better. Boy, my coordinates are not making sense here. I don't know if it's something that this Zoom thing has done, but I gotta, that just, it's the modern way of things. Okay, anyway, so there we have the keyboard. So if you can see, well, you can't see. I don't think, Ken, is it possible to share my image also?
What do you mean, the MIDI keyboard?
I mean, no, well, the video camera and the screen. Is it possible to do both?
Okay, yeah. So what you'd have to do is bring up the camera application on your desktop, because you can only share one video source at once. So if you just type in camera.
Well, actually, you know what? Let's see.
You should
Let's
be
do
able
that
to,
in a minute.
okay.
I won't do that yet. You guys can all see this keyboard though, right?
If people click on the speaker view in the upper right corner, it shows your camera when you're speaking, as well as the screen that you're sharing.
Wait, should I do that or should they do that, Jeff?
No, we do it, and we can also pin you so it stays on you.
Oh, okay, right. Okay, so anyway, you see that here. So we have this little MIDI thing. This is just something I added to the debug. So now we can just send it raw MIDI data, and it puts it onto a keyboard so you can see what's happening. Anyway, enough of that.
Excellent.
That was just on the way to something else here. So here's the big thing here. So this is a program I made that actually does, it has a few things in it. I'll go to the end here. It's not that long, but here's this last program right here. This is the whole MIDI thing that, I mean, it's all it takes to do MIDI. MIDI protocol is pretty simple, but what this does is it listens to a pin at the 31.25 kilobaud rate, and then maintains a 128 byte buffer of velocities for keys. And so it handles all the state stuff right in here. Again, MIDI is not that complex. If you get a note, an on node or note on command, then you wait for another one, you get the velocity, you get the note, then the velocity, then you go back to state 0, and you get note off. I don't know why they give velocity with note off, but anyway, it's like a 3-byte packet that comes in for everything. And so I maintain, let's see, where do I do?
It's for aftertouch. Some keyboards do aftertouch. That's what the note off velocity is.
Okay, now that would make sense. I don't think that has any application to like a piano, but maybe to a synthesizer. Anyway, so here it writes, it figures out.
And drums and percussion.
Yeah, that would make sense. So anyway, it suffices to say this thing here, it's a little PASM program that runs, and then it generates, it maintains this thing right here. It just magically, into that array, pop all of your key states. 0 means the key is off, and non-zero means it was hit, and that's the velocity. So I use that thing to kind of track what's going on with the keyboard. And then here I start that MIDI thing up. Now here I start this thing called the chorus up. And the chorus has like 16 voices. And in this code right here, I monitor those 128 bytes, really only, I don't know, 48 of which I care about. I'm just doing 3 octaves of keys. 3, 4, 5, 6, 4 octaves. And so this is the logic that just tracks the keyboard and then says, oh, assign a pitch to this voice and then start ramping it up. And then if the key gets let go, it ramps it down. So there's not like just immediate attack and decay, which sounds really, I don't know, like an old Casio keyboard or something. So that's all the keyboard logic there. And then down here is this chorus program. So this performs that tail and opposite tail fader function. And it also here, it's reading the microphone, and then it's outputting on 2 channels, left and right. Every time it gets a new voice assigned, it throws it on the left or the right speaker. So this is all there is to it. This is the data for it. Here's the code. This is the setup up here. It doesn't take much to do, but anyway, this realizes that thing. And it maintains 16 tail operations, right? So you can have 16 pitch bends going concurrently. And right here, this is kind of, we have a log and exponent function. And it's really nice because what you can do is you can take a linear value and run it through an exponential function and translate. In this case, this right here is really the log of 2. Because on a keyboard, you've got 12 notes, well, 11 to the next octave. And the difference between like C and the next C is double the frequency. So the division between adjacent notes, which means stepping up sometimes black keys to white keys, black keys, but linearly from like, 1 key to the next key in the next octave. The division, by the time you get through all that, you've doubled everything. But the geometric difference between each note is the 12th root of 2, which is like 1.059. So what this thing does is it calculates, here's the note, here's the offset. I have the whole keyboard set up so that middle C is my natural pitch. There's no pitch bend at middle C. Then here's the 12th root of 2. I could have put Q log 2 instead of this huge number, but I was just thinking about how it worked. And then here we put in the exponent based on how big our buffer is. And anyway, so this starts up a note. So when I run this program, I think I have a little bit of debug stuff in here. I have a thing that maintains the voices. So I'm going to get rid of this debug. I'll run this stuff. Okay, where'd I should have, my debug screen's minimized. Hold on. Okay, so what this is reporting is the state of the first, well, let's see, that's 16 now. We have 16 pitch bends, right? So there they are. So as I hit a note on the key, like if I hit C, it assigns the first voice. If I hit another key, another key, another key, another key, it assigns all these pitch bends. Then if I let the keys off, they cycle back to 0. So 0 state means key off, 1 means it's on, so ramp up to full volume, and then 2, which you see briefly, means ramp it down to 0, and when it gets to 0, kill that bend channel because we don't need it anymore. So it kind of dynamically assigns as I press keys. All right, so now I'm going to switch to my camera here. All right, back here now. So I have here a microphone, right? And this is going into the P2 chip. And then it's receiving MIDI, right? So if if I hit C, this is my normal voice pitch. Okay, there's a little bit of echo because the circular buffer is kind of big. But what I can do like key in a whole slowly like a C major 7 chord. So I'll just start counting. 1, 2, 3, 4, 5. This is a -7 chord, major 7. This is my normal voice, and then if I hit the C down, then I'm making my voice +1 down. I can add a 5th in there. Now it's a little more. If I hit a whole bunch of keys on the keyboard, I can, remember, this is my normal pitch. But if I put my hand on that amplitude gets really big. Let me, let's see, what do I start getting clipping? Well, I might be too complex. But if I hit a few, then I can sound like a whole bunch of people at once. Anyway, so it's like, I don't need this. It's like live pitch bending, like a sampling keyboard, but with live data. And you could dress this up and make it better, improve the envelope for the key and everything. But this demonstrates pitch bending concept. You can do many in parallel concurrently. What I found in doing this is that our ADCs are really, they're passable for, audio if you just want something simple, but for hi-fi, we really need to have Von Sarvash make us a little add-on board, that would go on the P2, something like this, which has maybe a really good stereo, at least 16, maybe 20-bit Delta Sigma ADC with a couple channels and a microphone input. Then we could get really high data into the chip. Because right now you could probably hear, like, if I just hit a bunch of keys, you'll hear a lot of noise. You hear that? Lots of noise. One funny little thing here about this program, I made a little thing here where we can add, well, there's a lot you can do with these audio effects. What I'm doing now is just multi-channel pitch bending, but I made a little thing here where JJ is just a little variable I threw in here. I take the right sample and we can feed it back into the microphone. And so when you do like effects where you're pitch bending, but then they're regenerative, so you're feeding the output back into the input, you get these funny runaway situations. So I'll comment that. Oh wait, I gotta share my screen here. Let's see. Portion of screen. Okay, we're still there.
Looks
I
good.
can see my screen now. Yeah, so I'm gonna comment out this little thing here that just, it can be add or sub, it doesn't matter. But what I do is I take the channel and I shift it right arithmetically. If I added the whole thing back in, it gets into positive feedback and runs away. But if I shift it down, then I can add it back in safely. So now it's like, folding some of the output back into the input. So test 1, 2, 3. 1. This is 1 octave up. 1. Test 1, 2, 3, 4. Well, it's not doing much. Maybe I need bigger buffers or something. But before, it was like, as it would bend up and feed back that in, there'd be like this shimmer that would just increase in frequency until it faded away. There's a whole world of things you could do with audio effects. Okay, let me stop sharing this screen here. Anyway, that's about all, I think. I can, I'm gonna fold this into a zip file and post it pretty soon. One other thing I want to show real quick.
So sorry, Chip, the noise that was sneaking in there, is that something to do with the hardware on the P2 itself? Or is it the output I'm using?
There was two noises. There's just room feedback, which was, muddying things up. And then when I did that mathematical feedback in the app, that thing, that was an internal feedback, but it wasn't doing what I had it doing before. But if you were bending downwards, it would like decay down in pitch. If you're bending upwards, it would decay up in pitch. When I was playing with it before, I was using headphones. And so I didn't have any kind of regeneration in the room, no feedback in the room. So it was a little bit different.
Because audio programming is actually one of the things I wanted to get into with the P2. So this is exactly on point for me.
Oh, good. Yeah, well, me too. I mean, since I was, long ago, audio is always, I was into audio before I'm kind of into hi-fi stuff here. We know these guys, these past lab guys. So I've been into this stuff since I was 10. And then I got into computers afterwards. So I'm always interested in sound stuff. And so the P2 was designed, it has these transcendental functions with the Cordic. Also, it has log and exponent. And you can see here how we're using exponent to actually convert a linear note number into a frequency that becomes a musical note. So there's all kinds of fun applications. But what I see we need now is we need a better audio input, because we can do really high quality computations, but our ADCs are not so good for they're not that clean that we want for audio.
These are the ADCs built into the smart pins, you mean?
Yeah, every pin has one.
Right, okay. So they're good, they're just not high-end audio good.
No, right.
Okay.
And maybe we'll get it, maybe we'll figure out how to make them better in the future. But for now, I mean, maybe separate, 20-bit ADC chips exist for reasons. I mean, you have to have quiet power supplies and everything to get the performance out of them.
Chip, if you guys have one of those Coyote guitar processors that were made with a P1 floating around your office, you might have a look in that, because it's got nice ADCs in it.
Oh, okay. Did you get?
And that was with a P1.
Oh, the P. Yeah, boy. I don't know that I've had one of those. But I think our DACs are passively good for output, but our ADCs are not so good for input. Yeah, Jim, are you going to say something?
Yeah, I've got one of the Coyotes if you want to do a teardown on it. I think David Betts.
Well, these days that was okay. That thing was made probably 10 years ago, right?
Yep.
I mean, not that it's at all old in a sense, but I noticed that ADC chips are getting so cheap. You can get, good quality ADC chips now, like 2-channel, I think 20-bit for like $1 or $2. It's just crazy. I remember going to a trade show once and they had this like 50 kilohertz 16-bit ADC module, and it was thousands of dollars. And now, it takes 1,000th of the power and costs 1,000th as much.
That is true. Yep.
Chip, can you talk about audio generation? Just how do we spit out a sine wave of any frequency or a triangle wave?
Well, there's a whole bunch
wave that we might have in an analog synthesizer.
Well, you can, for audio level stuff, you really want to compute it and then output it through the DACs. And I think our DACs in the 16-bit PWM mode are quite good. I mean, they're pretty decent. I've had the headphones on and listened to them, and I don't hear any background noise, and the dynamic range is huge. So what you'd want to do for audio stuff is you want to synthesize, you want to compute your samples and then output them that way. If you're doing higher frequency stuff like radio frequency, you can use the IQ modulator, which is part of the what do we call it, the color space converter, or you could use the direct digital synthesis. They're both good, but the IQ thing can turn on a dime as far as its modulation goes, but it's lower resolution. It's meant for generating the chroma signal for color on NTSC TV or PAL or whatever, but you can repurpose it for RF applications too. But anyway, for music synthesis stuff, things that our ears are going to hear, you would compute the samples, and you could use the Cordic to get your sines, and all of your envelope, because you use sinusoidal things and all kinds of stuff. Like a Hanning window is basically like, you know, a 1 minus cosine divided by 2, and it gives you a nice, you know, bell curve. So all those envelopes, and you could build low frequency oscillators, because usually in sound effects, you don't just have the audible frequencies, but you also have a lot of low frequency oscillators that are like, you know, they're cycling over multiple seconds to do things like for flangers and whatnot. But we have the chips built to be able to do all that stuff. Everything is in there that you would need to be able to do all that. And in time, I'm sure we'll write more, you know, synthesis stuff. One thing, oh, go ahead. I will share my screen again. I wanted to show one more thing. You can see this. There's been a lot of discussion over how does the hub memory thing work. And let's see here. If I can drag this thing down, this little program here shows just a little bit of spin code, but it uses the plot display to actually demonstrate how the, you know, what the relationship is between the hub RAMs and the cogs. So I think it'd be good if, you know, in the future, we could use these kinds of methods to document things, because it's even, you know, as much as a picture is better than words, this can be better than a picture. And the code that drives that is this right here. Whoops. Didn't take much to do that, just this loop here. And the way it works in this case, I set up this plot thing, and I just call it my plot, and I tell it where. I do a delay here, which we're not going to need soon because we're going to get all this serial onto its own thread. Jeff's working on that. And then I set up some basic rules of operation. Like I say, a unit circle. I want polar mode. A unit circle is 128 divisions, which means we can feed like 0 to 127 or any supermodulus of that and get those angles. And I want an offset of 32 to put 0 at 12 o'clock, because 32 is 1/4 of 128, right? Then I set up some stuff. And then here, the way something like this would work is you clear the debug window, which doesn't promote it to the window canvas yet. Then you can do all your drawing stuff. And then when you're done and you've got that new window done, you just do this to push it out to the actual window that you see. This way you get no flicker or anything. So if I didn't put, like if I turn this update thing off, before I destroy this, let me call this something else. All right, I'm gonna get rid of the update thing here, right? So we're not gonna update the window, we're just gonna draw it as we go, and we're gonna get rid of this thing, we're not gonna update the end. Now when I run it this way, I don't know if you're seeing all that, but this is not what you want, right? But by being able to gate the promotion to the window, you can do really nice animations that don't have any flicker.
Yeah, without the double buffering, that's a hot mess.
Yeah, sure it was. That's how it started out. It was messy. And I found that, you know, in some of these cases, let's see, Spectrum demo. 1, 2, 3. In cases like this, you can see this little display here. Let me get rid of all this noise. There, so here we have the spectrograph. I actually have the spectrograph function built into the display now. So if you just feed it samples, it can do the spectrograph or FFT for you, and it can do this in, this now is like in linear mode, but by putting in, let's see, let's see, where do I assign the spectrograph? Oh, it's actually using a bitmap for this one. This was before I had the spectrograph. I think it's called spec demo. Okay, let me run this one. Okay, yeah, so here I've added some new coloring modes too, where we can fade from like white to a saturated color or black to a saturated color, or from black through a saturated color all the way to white. And that spectrograph was being done in Windows. Oh, but what I was gonna say is I found that the draw time on these things is quick. Like a lot of these big windows could be like 600 by 600 pixels, and Windows completely draws them in like a millisecond. So you can get super fast throughput for these things. Okay, there's one thing. Oh, here are the new color things I added. So the bottom two are 8-bit modes, and then the top three are 16-bit modes. But you can see this first one fades from black to saturation, then from next is white to saturation, and then this one goes through saturation from black to white. And then this is a mode that goes through a single, this is an 8-bit mode, this one here, that goes through a color from black to white. So you can do all kinds of cool stuff. And that's what I was using in that one spectrograph display. So I've been adding lots of these modes here.
Yeah, I was able to download the YY and run the egg beater. It looked pretty cool. And then Windows Defender wanted to get rid of Peanut again. We're still having that problem.
Yeah, we don't know why. I'll put another one out when this is done, and I don't know, we'll just see what happens. Maybe probably will get deleted if it's back on the kick of deleting all our stuff again.
Yeah, I thought Jeff took care of that. But it's back to haunt us.
Yeah.
There's workaround.
Yep. Anyway, we can talk about whatever you guys want. Ken, do you want to? Are you still there, by the way? Oh, Ken's on the phone. Look.
It's
anyway,
all eavesdrop.
Yeah. I'm sure if you zoomed in on people unawares, you'd probably find someone picking their nose, right?
Or worse.
Yeah.
Hey, Chip. When you run these Peanut programs, is that downloading them to the P2 and then the P2 streaming back the data to get rendered on the PC?
Okay, here's how it works. Okay, let me share my screen again.
Yeah, it's a serial protocol feeding back to a program running on the PC that actually does all the drawing.
Yeah, the PC has the code that actually does all the rendering. All we do is just send a little bit of data out. Like, you see this program here? Let me make it bigger.
Yeah.
Okay, so if I do a list on this without debug, this is how big the program is, right? With the debug, it's only a little bit bigger. You see this? It grew a little bit because there was some stuff that it had to compute to feed the debug. Mm-hmm. But all this stuff, the rest of the data right here gets squirreled up into the write protected top 16K of the 512K byte RAM. And so we offload, it has minimal impact on your program footprint, but when this thing runs, so I'll run this, right? Let's see, Control F10. Let me get this window up here. See this thing? It's just sending out, okay, there's a better one. Let me see, was it the clock face? I did this one thing, it was like a little clock. Boy, what did I call it here? It was a nice little succinct example. I want to find it. And it shows you everything in one little bit. Okay, let me grab it. I'm going to go on the interwebs, if I can find my my menu bars, like everything's missing. Well, here we go. I'm going to grab it off the forums. I posted it there a few days ago, and it's very simple, but it's like a perfect little example of how it works. All right. Okay, just a minute here. Almost there. What I'm going to do is just grab the, I'm getting close. Here we go. Okay, so, oh no. Wait, debug plot polar. Okay, that's what it's called. I can find it now. I was going to copy and paste the program, but it's like a screen image. Can't do it. Okay, debug plot polar. Let's see. Hopefully this is it. Oh, it got big and ugly. I don't know what happened to it. Maybe I could reduce it here real quick. Hold on a sec. Well, what happened?
This is kind of good because it gives me a view of some of the commands that you can send Peanut to interpret. You know, things like my plot, you know, that's a plot window that you set up, and you're giving it various parameters and things like that.
Right. Yeah. All you do is there are many different there are like, I think now 11 or 12 different display windows.
Mm-hmm.
And what you do is you start off with a display window and then you give it a name, right? And then thereafter you use backtick name to feed that window whatever kind of data that it expects.
Cool.
And it's all kind of like simple English. I really want to show this one thing. Let me, man, why did I saved over the same file, so, but this is so simple. So let me save this, and I want to reduce it down so you can see just, this is called plot polar clock.
Hey, Daniel, if you download the latest Peanut archive, there's a file in there called Debug Displays that you'll want to take a look at that has all the mnemonics for debug.
Okay, sweet, Jeff. Thank you.
Okay, so let's see. I'm just going to recreate the whole thing right here. Okay, maybe you guys could talk amongst yourselves for just a moment here while I type this in.
Hey, Peter, you on?
Hello, Jim.
Hey, yeah, I saw your write-up on the P2 stuff. It looks good. We're getting close, huh?
Yeah, well, you know, I just want to get it out. You know, it's just, you know, a bit of this and a bit more of that, and, you know, all these different boards, and I've rationalized it all now. So, yes, so I've just got a set of 4 different types of boards next week, and then I've got some other boards coming after that. Yeah.
I'll be ready. I've got a new address. I'll have to give you the address for North America distribution. So it's in the same country.
Yeah. So once I check out those prototypes, then, you know, I really just want to get a whole big batch of them done, and that, because I don't want to worry about production myself. So I'll just get them made up, and then I can ship them out. You can have a whole box full of them. Yeah.
I'm sure people will pay more to have them pre-assembled, myself included.
Well, I think it'll work out cheaper in the long run just to do it like that. So
yes, indeed.
Might be off the price.
All right. Well, I'll be here.
Has anyone spent time with HDMI on the P2? I was looking at Chip's code. I didn't want to disturb him while he's coding this.
No, I'm done. I'm already done.
Well, I'll wait till you're finished presenting that.
Okay, you want me to show that? Okay, so here we go, right? So this is a really simple little thing. So you have to have at least 10 megahertz of a stable time base to do debug. So here we set up, we want a plot window. We're going to call it my plot. Here we position it on the screen at 300, 2000, and we want it to be this big. I do a delay. We don't need that soon. And then I set up some stuff. I say the offset is 150, 150, which is the middle of the screen, right? X and Y, that's the center of 300, 300. And then I say go into polar mode, and I want 12 units in a circle. And negative means clockwise, because positive naturally means like always counterclockwise, the way math
like
works.
radians.
Yeah, instead of radians, now 2 pi equals 12.
Yeah.
And because it's negative. And then we say minus a third, that means minus 3 means back up 1/4. So go 90, what is effectively 90 degrees to put the 0 degree point at 12 o'clock. And then down here, we just go, from 1 to 12, we do an oval fill. We're in polar mode now because we put this polar thing here. So we go 100, that's how far out to go from 150, 150. So it goes 100 out, and then this is the angle here, right? An angle is going to go from 1 to 12. And then 30, 30 is the width and height of the oval, which means it's a circle because those are the same. And then text, we want, so it leaves the XY pointer right in the middle of where you last drew. And then the text is by default center justified on both X and Y. So then we just say, here's our number, sign decimal, I. And then so look, when we run this, you see two things. You see the window down here, right, where it drew a clock face, and then you see what actually got sent out to the PC. So these first two things in the window are just, it first boots, then it starts up the interpreter on the second init, and then it says, okay, start up plot. I want it at this position on the screen. I want it to be 300 by 300. And then I'm going to set things up. I'm going to set my offset at 150, 150. And then I want to go into polar mode. And I want, these metrics for my angles and offset. And then I just give it these commands. It says oval fill. So radius is 100 in all cases. The angle stepping from 1 to 12. It's 30 by 30. That's going to make a circle, not an ellipse. And then here's the text that it prints out. So you can kind of look back at the source code and see how that, how that worked. But what I'm going to, yeah.
Can you throw a delay in between each of those lines and then rerun it for us?
Oh yeah. Watch if we do like a set. Oh well, I can just do that right here. Let's see. I can just say wait ms 1000, right? There. And see the code for this, if we look at it with the debug, so you can see that the first section here is the actual byte codes that the interpreter executes. And then this is the debug data that got squirreled away. This is all that special textual stuff.
You just got pointers to each of those in the code.
Yeah. Yep. And then if we get out of here and we just look at, if you compiled without debug, this would be the whole program. So the point of these debug statements is they only get compiled if you're compiling for debug. Otherwise, they get ignored. So you can stick all kinds of like little, not just this backtick convention is for calling up these special display windows. But if you just wanted data to report to the, green debug window, that doesn't take any special effort. You can just stick a debug statement anywhere in your code, and when it's encountered, it'll report that data. And it's it works in PASM too. In PASM, it takes one instruction to insert a debug, and then that debug does a break, which references the data that's squirreled away up in the top. So the debug interrupt then unravels all this stuff and then generates the text messages to send to the PC. So the PC just, interprets all these backticks as, oh, that's a special message.
So one of the things I'm seeing too, Chip, is that you've got a second line of the plot window configuration in there. I think that's the first time I've seen you do that.
Oh, well, this isn't, see, this convention is the same as runtime. So at any point in your execution, you can change your offset and you can change polar, or you can put in Cartesian and just go Cartesian mode too.
From that point forward.
So it lets you dynamically switch things up depending on what kind of stuff you want to draw.
Right. I'm also, are the Cartesian and polar, and are those new in the next release? Because I'm not seeing them in the displays doc.
Oh yeah. It's all in the thing I'll put out today, but I have yet to document this in the, in the main Spin 2 document.
Sure.
Is there a way to configure the serial parameters in case, for example, in the future, you might want to actually put like some kind of debug logger on a product in the field, even if it's not connected to a PC?
Yeah, you can go like this. You can say, I think this is the debug. This is already documented. You can say debug pin equals like 0, and it will send out all these messages on P0.
Okay, thank you.
And you can also put like a debug delay, because let's say it's going to take you a few seconds to start up. You can put 2,000 milliseconds. That will wait 2 seconds before it starts anything. So like if we just do that, we don't want to change the debug pin. But if I run like this, see 1, 2, boom, then it does it. In fact, Steve in Morocco, I haven't fixed those problems you noticed yet about if you redirect the debug to go elsewhere, it needs to not open up our window. I'm going to get that straightened up.
Nice, thank you. Yeah, I redirected the output, and I'm running a Python interpreter for the debug output and drawing these same windows for just a couple of the window forms at this point over Raspberry Pi.
Oh, cool. Okay.
I see all this stuff and I'm thinking I could write a game with all that output.
Yep. Well, yeah, Windows has all these primitives built in that do a bunch of stuff. All you got to do is just kind of give them access to that, and because it's all pretty generic in nature. I'm sure other operating systems have the same stuff. Here's what the thing I want to do next is I want to make it so that if it sees a backtick at the beginning, it'll automatically go into the special mode where there. That's how you're gonna type it in the future. You guys see that? On the second line here, let's see. Right here.
Outermost line.
Yeah, it's just more condensed.
Yeah, so what I'll do, the debug thing needs to be the way it is for normal stuff, but for these display windows, I'm gonna look, if the first thing I see is this backtick, I'm gonna go to this alternate syntax thing where it's gonna treat everything as a string, and then subsequent backticks are gonna have to be followed by one of these number printing things, or just something in parentheses, which is an expression, which will then resolve down to a character. But see, that's going to simplify things quite a bit.
How are you going to handle your control sequences then?
You would just put them like control sequence, like control characters.
Correct. Your tabs, new lines, things like that.
Oh, you could just go like this.
Gotcha. Okay.
Yeah.
I'm writing a parser which has me thinking about this. And because you have the 2-line control for the window, understanding whether update is a config value or a feed value is going to be a little bit tough.
The way I did it is I have some special keywords like these. Yes. These are like display type words, right? But then everything else, including, oh, no, no, not that. Now this is an unknown. This is the name that the user gives.
Correct.
Right? So this is a display type, but every other thing I just call a keyword. So position, size, polar. And so my parser doesn't know if they're in, if what the guy typed made sense. Only later downstream does it go, oh, this doesn't make sense, don't do anything.
Right, I understand that. For instance, in the plot window, you're telling the window itself to run in update mode in the case of putting it out when you're setting up the window, and you're telling it when to update with the same keyword.
Right, that's why they're just, see, I started out having different types of words, but things that would be only viable, only allowed during parsing of the initial instantiation command, and then other things that were for the feeding. But what I did is I just genericized all the keywords, and I just allow everything, but then later as the data gets received, the window has to go, okay, does this make sense for me or not?
Right. So what you're suggesting is that update on configuring the plot window would have to occur in the very first line for it to be an update window.
Yes, you can see in the case of the instantiation, like this line here, if update were to appear here, it would set a flag.
Yes.
Because this is unique because this is not a username, this is a display type name.
Correct.
So,
but you've got some configuration parameters such as offset and polar that are also configuration, but they're embedded in the feed, if you will.
Yeah, and I mean, I could have made it so you could have done, I could have allowed all this. I mean, I would just write a few more lines of code and I could allow all this in the instantiation line as well, not in the feed line.
Gotcha.
I could do that, but I made these at least dynamic so that as you're drawing a screen, you might want to like move over to another location of the screen, draw some stuff with some relative coordinate setup.
Yep. Yep. Fully understood. I'm just trying to separate the terms. I'm not advising anything for you. I'm just trying to ask you questions so I understand what you're intending.
Yeah.
Right.
So just generic keywords. There's only two types of words. There's the display types are special, right?
Yes.
Then there's the usernames, which are unique. And then there are keywords which can appear in the instantiation and the feed lines.
Nice.
I started out discriminating, but then realized, oh no, do I have to make another word that's so similar? I thought, no, I'm just going to make them all generic keywords.
Gotcha. Yep.
So this is the next thing I wanted, just a simplification for, kind of this because it is tedious to go, okay, I need to generate, I'm going to have to make a string with all this junk, and then I need to output a value, so I got to end the quote, put the commas in, that's business, start a new quote up.
Yeah, that's nuts.
And for the normal debug output, that's okay, but when you get into these displays, you need a simpler way.
Mm-hmm.
Well, hey, Chip, if I were to make you some sort of ADC board, I'm assuming the ADC would talk via SPI.
Yeah, anything.
Yeah, that's typically how they do it. Would you be able to show me how I could write a simple program to talk SPI?
Well, there's so many ways you could do it. You could bit bang it, and or you could use the well, the way I did it for like the let's see here, for the flash loader, I actually use the streamer because our streamer now can actually grab pins, and like at a cadence you set, it can grab those pin states, assemble them into bytes, and then write them via the FIFO into main memory, like DMA.
Yeah.
So it can automatically just do all kinds of stuff. So that's how I did the programming. And like, let's see, where do I write the code? Let me see here. Yeah, and this is so, I go right over it because there's almost nothing here, but these lines right here, that X in it tells the streamer to start outputting data that's going to be programmed. So it's going to output 256 times 8 is what, 2K bytes? 2K bits. So it says start outputting 2,000 bits. And the FIFO is already, set to some place in memory. So it's going to get the data from there. And then this thing here, the WY pin, that is a pin that's already in transition mode. So all we got to do is just feed him how many transitions we want him to do. And we've already set up his period and everything. And so once I do these two commands, this one starts the streamer. This one generates the SPI clock. And then this guy just waits for the streamer to say he's done, knowing that we finished the job. So by the time we get to that, after that third instruction, the whole job's been done. So all those bits have been read from memory, shifted out, and into the flash.
Now, that doesn't toggle. Oh, does that toggle so that all that does is toggles a clock pin, but we also need to tie data into this as well.
Well, yeah, see, the data is coming out of main memory. So somewhere up here, well, no, in X emit, let's see, if we go to R mode, where's that value at? Right here. Okay. This value here. So this says, 1-bit mode. See that 800? There's our 2K bits, right? See that right there?
Yeah.
That's our 2K bit block. The bottom 16 bits are how many to do. And then this is the mode. This is like a 1-bit, into main memory mode. And then let's see, I'll go back up to that code. So here it is. So we start the streamer, and then we start the clock up. And the timing was such that everything jived. Like I might have had to add a no-op or a wait X instruction in there to synchronize everything, but it so happened in this case that the timing was like lined up. So I start the streamer, start the transition pattern on that SPI CK pin, and then the hardware just does it all. And then down here, I wait for it to be done, and then when it's done, I return.
Cool.
If you guys are specifically targeting audio, there's a whole series of audio codec chips. And if you look into the I2S protocol, it's a very simple way, but then you get a whole bunch of audio goodies for free, including you can have ones with headphone drivers built into the chip and stuff.
Ew, that's cool. Yeah, that's what we kind of need. So SPI bus, Daniel, it's just bit shifting. It's like a clock. SPI might be like is that kind of a biphase communication, Jonathan, or how does that work?
Yeah, the I2S, they've got like a word clock. And so in the easiest mode, the word clock, when it's high, you'd clock out 24 bits of like your left channel, and then it could go low and you'd clock out 24 bits of the other channel, or they have like a DSP mode. So there's like an extra pin, like a word clock, a bit clock, and then your actual data pin.
Oh, how interesting.
Yeah, it's simple anyway, Daniel. It would just take a couple of instructions and it would just happen. And
sure.
You wouldn't even have to worry about the software. I mean, you may not know at this point what to do, but we could write it together in like 10 minutes and make it go.
Sure.
And it would be like several lines of code.
My concern would be, making the hardware is just one side of it, but then we got to make sure it works too. That's the software side.
Right. Right.
If I can say, Daniel, if you're not using the streamer like Chip was just showing, doing SPI is dirt easy, as Chip pointed out. And to be honest with you, after doing a bunch of stuff lately, it's just easier to write it in assembly than to use the smart pins. There's actually less code to write a SPI IO in assembly than to set up and use the smart pins.
Gotcha.
Yeah, but sometimes if you could, there's a lot of you got to switch into granny gear when you want to employ a smart pin. It's going to do the job for you, but there's like a lot of little persnickety detail that you have to kind of work out. And once you do that work, like how I did in this flash case, it's real simple. But at the outset, it's like, oh my gosh, what have we got to do? Look through the documentation, okay, code it, you got to do a write pin, maybe a WX pin to configure it. And then you put the DIR high to turn it on. And then you give it a command through write Y pin or something, and then you see what it does on the scope. And so it'll do it for you, but it is easier just to write the assembly code.
Yeah.
But now check this out. That last thing I showed you was where we were outputting, right? We're outputting data to the flash. So here's where we're inputting data from the flash, right here. So the WY pin, we're already in, the streamer's already queued up from that write fast instruction at the top.
Yeah.
So it's ready to spew data out of its FIFO from main. No, this is data coming in from the pin. The other data was going out to the pin. This is coming in from the pin into hub RAM. So the write fast up there set the thing up. And then when we do the WY pin, this begins the CK pin transitions, right? Then I had to put a little wait in here. We needed to wait 5 clocks. Then I initialize the streamer with the command, and then I wait for the streamer to be done. Now in this case, it's putting in like as many as will fit into 15 or 16 bits. It's a huge number. It's going to read in like almost 64K bits. So that's 8K, almost 8K bytes. It's going to stream that right into hub RAM from the flash chip, and it does it just right here with a few setup instructions before that.
Cool. This is the loader program. Gotcha.
Yeah, this is all built into the interpreter. So or anything when you do like F11 or control F11 for debug, it takes it and it shoots it down into the flash.
Yeah.
And it's real quick. Like if I want to, let me get a program here. Like what do we have? Here's I don't really have anything that's that sizable. Everything I make seems to be kind of small. It's got debug scope. Wait. Test. Let me see. Bigger program. Okay, so here's something that is, it's, well, 2.4K or so. That's all it is. But see, if I want to program this in, I can hit F11 and there. It just, in that time when you set window up, that was compiling, downloading to the flash, and then the flash reboots.
Wow. Huh. Pretty impressive.
Now I've got something in there that is always going to make noise. Let me write something else.
Hopefully it's not a vocal track.
All right. Okay, there. Now we're quiet again. That 2-second delay was there. And I see once I program, I hit F11 to program that in. I can hit F12 to completely kill the debug, but since I programmed it into the flash, if I open up debug and I reset, there it reloaded everything because the debugger was just waiting, right? So let's see, open up debug, hit reset on the board, there. So the debug was just waiting, and see, as it got like this backtick plot, it goes, oh, the guy wants to open up a window, so do it. Then it took the commands in. So it's kind of agnostic. This thing, we could take this program and make it so it just works with anything, because these are just serial messages.
I have a couple questions.
Yeah.
Okay. So I was working with HDMI. I was looking at your code, Chip, from the documentation in the web page on Google Docs. You had an example of a HDMI program that output a 15-bit color bitmap, if I recall.
Oh, right. Okay.
Yeah. And I would have a component version of the code that I'm writing, but I'm trying to write the HDMI version, and I think I'm pretty close. But I was just curious about the you have like sync 000 sync 001 in the code.
Yeah.
It's like these like magical bit patterns for hsync vsync. I was wondering where those came from.
That's HDMI. So we're just doing what it needs. Let me pull up an HDMI thing here. Here's 1280 by 720. So
Chip, while you do that, I'm going to stop the recording so people can ask all kinds of other questions too.
okay.